Imagine standing at the edge of a black hole, watching light itself stretch and vanish into darkness. Here, Einstein's relativity predicts one picture, while quantum mechanics insists on another. Both can't be right in this place, yet both have passed every test we've ever given them. Which one survives, and what new rules might emerge if neither does? That collision of truths is the very problem of quantum gravity, and it could rewrite what we mean by space, time, and reality itself. When physics collides. When two theories each claim to describe the world perfectly, you expect them to at least agree on the basics. Yet, right at the core of modern science, we face the opposite. Two systems, each precise and successful, point in different directions the moment they overlap. General relativity paints gravity as a smooth bending of space and time, while quantum mechanics reduces reality to jitter, chance, and probability. Each operates with absolute clarity in its own territory, but in the same place, in the same instant, the two seem to speak entirely different languages. Relativity handles the colossal. It governs planets swinging around stars and galaxies drifting across the cosmos. In this picture, space is like a flexible fabric warping near any concentration of mass. The Earth rolls around the Sun because the Sun reshapes this invisible medium, pulling paths into orbits. Quantum mechanics, on the other hand, handles the minuscule, atoms, electrons, photons. Here, the rules harden into limits. You cannot pin down a particle's exact position and momentum at once. Outcomes become a matter of statistics. Instead of certainty, every future holds a spectrum of possibility. These two visions do not just differ in focus. They embody incompatible assumptions. One insists on a continuous flowing geometry. The other insists on abrupt switches and indeterminacy. Most of the time, the conflict is hidden. You can use relativity to plan spacecraft trajectories. You can use quantum mechanics to describe chemical bonds. Each works, yet both rely on being confined to their specific arena, avoiding direct contact with the other's domain. But nature does not politely separate scales for our convenience. At extremes, the core of a black hole or the first instant of the universe, both theories must act at once. And here, instead of harmony, we find contradictions. Relativity predicts a collapse into a singularity, an infinitely dense point. Quantum mechanics forbids infinities. It signals that something is missing in the description. The result is not just uncertainty, but breakdown. Equations, so trusted elsewhere, simply give nonsense answers. It's a bit like having two maps of the same city. Each map covers nearly all streets correctly. For the downtown, perhaps the first map captures every alley. For the suburbs, the second handles every detail of the roads. But at the edges where downtown meets suburb, the maps refuse to line up. Roads veer into empty space. Bridges stop at rivers that aren't drawn. On their own, each map seems reliable. Together, their flaws reveal themselves. Worse, you cannot stitch them into one coherent whole. Think of the smoothness relativity promises, space as a perfectly woven fabric, flowing, infinite in principle. And set against that, the jagged unpredictability of quantum mechanics, where events rely on jumps, where an atom may transition without a clear path. The two sets of rules belong to different realities, yet everything we see belongs to one universe. The tension is not abstract, it is guaranteed to occur in severe environments where both magnitudes of scale press together. Consider a black hole's event horizon. Particles flicker in and out nearby. Gravity compresses at full strength. Relativity says matter collapses toward infinity. Quantum mechanics says no such infinity can stand. Or consider the Big Bang. Relativity describes a smooth beginning expanding outward. Quantum uncertainty says the notion of a perfect starting point cannot exist, that time itself could not be smooth in that first instant. We cannot reconcile these accounts with the tools we have. These clash points serve as unplanned experiments. Nobody constructed them, yet they stand as natural stress tests of our knowledge. When formulas break down, they signal that a deeper principle must exist. It is not unlike a bridge built with an incomplete design, which works fine under small loads, but splinters under weight beyond its tolerances. The collapse points straight at what builders overlooked. In the same way, singularities expose where physics lacks a unifying plan. So when we talk about when physics collides, we mean exactly this. Two foundational laws, both validated again and again, reveal a fracture line when tested against extremes. And unlike in engineering, where you can avoid overloading a bridge, in physics we cannot avoid black holes or the question of the universe's birth. These are not optional edge cases. They are part of reality itself. The lesson here is stark. Relativity and quantum mechanics shine as independent guides, but neither can stand alone when matter compresses beyond atomic scales, nor when time compresses to its first fraction of a second. The conflict is baked into the very shape of physics. And while almost everything around us is too mild to trigger it, the cosmos itself guarantees we face it where scales collide. Once understood, this failure of maps is not a disappointment, but an opportunity. Scientists do not run from singularities, they scrutinize them. Where theories snap under pressure, innovation is born. Each contradiction becomes a signal, like a beacon guiding us to what remains hidden. For the unification of physics, these extreme domains are more than puzzles. They are clues to how nature works at its deepest level. You can think of these regions as frontiers. At a safe distance from a black hole, our current theories hold. As you approach the edge, relativity still describes orbits with precision, yet quantum mechanics still governs the particles racing in. At the crossing point, both should combine, but instead explode into contradiction. That precise location is the frontier, the unseen territory any true theory of everything must conquer. And so the unavoidable truth is that these collisions matter most where gravity intensifies beyond limit. That makes black holes more than just dead stars or cosmic oddities. They become essential laboratories, places where the two maps must overlap. Here is where the mismatch of smooth geometry and quantum jump cannot be avoided, cannot be brushed away, but instead forces itself on us. To understand this edge, we must craft a new lens that contains both visions at once. This shift is what propels the search for quantum gravity, not curiosity alone, but necessity. Because no matter how accurate today's equations seem, the universe has built places they cannot enter, and you and I must follow into those places anyway, which means if we want to continue the story of physics, if we want to describe reality without fracture, we are compelled to face black holes head-on. Gravity's stubborn resistance. In physics, we have a clear recipe for handling forces. Start with a field that fills space. Treat the particles that carry that force as excitations of the field. Then let quantum rules govern their behavior. That recipe delivers quantum electrodynamics for the electromagnetic field and quantum chromodynamics for the strong nuclear force. The weak force also fits into this playbook. Each of these theories makes predictions that match experiment to astonishing accuracy. It would appear almost certain that gravity, being the last great force, should fall into line with this same method. Yet when we try, gravity resists. Think of the approach. We imagine a particle, the graviton, as the quantum packet of the gravitational field, just as the photon is the packet of light. We allow that graviton to interact with itself and with matter. Calculations then proceed by adding contributions from different processes. Each contribution can be drawn as a loop, particles traveling paths, sometimes looping back into themselves. For electromagnetism and the nuclear forces, these infinite sums can be tamed through renormalization. Certain infinities appear, but with careful bookkeeping, the theory absorbs them into parameters like charge or mass, and the numbers that remain are finite. But with gravity, this trick fails. Instead of isolated infinities that can be contained, the calculations erupt into an endless cascade of them. It is like trying to divide numbers that lead to a zero denominator. At first, the formula seems well behaved, but the moment you push your calculation, nonsense floods out. If you imagine entering sums into a calculator, some fractions give you useful answers. Then one line returns, error. Gravity's quantum loops behave like that error message. Even the tiniest loop diagrams in a graviton calculation already give values that diverge toward infinity. Stack enough of them, and the framework collapses entirely. This property has a formal name, Nonrenormalizability. It means that when you attempt to clean the infinities, they do not consolidate into a finite set of corrections. Instead, each new stage brings new infinities, requiring new fixes. The repair effort never ends, and your theory loses predictive power. For the other forces, quantum field theory provides a consistent mathematical machine. For gravity, the same machine seizes up. Why should gravity be different? One reason is that gravity couples to energy itself. Other forces have charges, electric, color, weak, isospin, that are specific properties of particles. But gravity responds to everything that carries energy, including the energy stored in the gravitational field itself. That self-interaction feeds back without limit, leading to runaway behaviors. In imaginative terms, gravity refuses to stand still long enough to be pinned down as a manageable quantum field. Suppose we attempted a tiny step. We try to calculate just the first correction beyond simple classical gravity, one small quantum loop of gravitons interacting. Already the integral that represents their paths explodes into infinity. Unlike in electrodynamics, where this infinity can be renormalized into a shift of electric charge, here no such fix works. You remove one infinity and another takes its place. It is like scooping water from a leaking boat, only to find each scoop makes two new holes. The failure is not a fluke of calculation. Physicists return to it again and again, trying different arrangements, different ways of applying renormalization. The outcome stayed the same, no conventional fix. That is why the problem of quantizing gravity is still open. It is not neglect or oversight, but a deep structural issue in the mathematics itself. The implications are large. For the electromagnetic or nuclear forces, once built into quantum field theory, the framework became incredibly successful. We could predict the magnetic moment of the electron to many decimal places. The standard model of particle physics emerged as a precise working theory. Gravity, left outside this unity, stands as an exception, and exceptions in physics often point to deeper truths waiting to be uncovered. If you were to insist on treating gravity with the same machinery, you would drown in infinities. You could set cutoff scales to stop the sums at some energy, and the answers would look finite temporarily. But physical predictions would become unreliable. Push the cutoff higher, and the bizarre results return. This signals that the problem is not with technique, but with assuming gravity is simply another force like the rest. So perhaps the mathematics is not broken after all. Perhaps it is pointing with insistence to a missing element. Non-renormalizability could be a symptom telling us that space-time itself cannot be treated as just another quantum field. Maybe space and time do not exist at the smallest scales as smooth continua, but instead require a different ontology altogether. The clash between gravity and quantum field theory might be our best evidence that the building blocks of reality are not what we thought. At this point, a quiet insight emerges. If a tool works for every other problem yet fails dramatically on one, the failure is not noise, but signal. Imagine an engineer testing a design where every component passes except one. That one component then dictates the direction of improvement. In our case, gravity is that component. Its resistance guides us toward frameworks beyond standard quantum field theory. This is what makes the challenge so tempting. Those infinities at the heart of quantum gravity are not useless scribbles. They are warning lights, marking the limits of current imagination. To this day, when graviton loops collapse into nonsense numbers, it forces us to ask whether space-time itself is the right stage for the drama of physics. Perhaps the stage must be replaced as well as the players. Think carefully about what this means. Electromagnetism, strong and weak forces fit into one scheme. Gravity does not. That mismatch represents a fundamental lack of unity in our descriptions of the universe. And history tells us that when unity is missing, searching for it transforms science. The resistance of gravity prompts all later theories that try to reshape space-time, whether by adding extra dimensions, replacing particles with strings, or quantizing geometry itself. So when you hear that gravity resists quantization, it is not just a computational nuisance. It is a profound obstacle that defines the frontier of modern physics. The fact that infinities appear at every attempt tells us that the smooth map of space-time has limits. Our equations betray it. The path forward, therefore, lies not in patching the old maps, but in daring to draw new ones altogether. This realization pushed early physicists into bold directions. If the standard recipe breaks, then the recipe itself must be rethought. The stubbornness of gravity became the seed from which speculation grew about new symmetries, hidden dimensions, or even space-time, built from discrete chunks rather than smooth lines. The search for unity could not proceed without confronting this resistance. And it is this refusal of gravity to be treated like the others that led directly to the strange and imaginative proposals that followed. Dreams of a unified map. Why would a scientist who had already reshaped our picture of the cosmos refuse to stop? For Einstein, the answer was simple but unshakable. He held a conviction that the forces of nature were not separate parts of reality. They were facets of a single whole. Relativity had shown that space and time were not detached, but fused into space-time. Gravity itself was no longer a mysterious attraction at a distance, but the bending of that fabric. If space-time and gravity could be unified, why not extend the vision to the other known forces as well? For him, electrons deflecting under electromagnetism should be linked in some yet-to-be-seen geometry. Nature, he believed, could not be a patchwork of unrelated laws. It had to come from one woven pattern. This conviction was more than logic, it was aesthetic. Einstein trusted that the universe possessed simplicity at its core, and once uncovered, the laws would fall into place like parts of one equation. He thought elegance was not just pleasing, but a sign of truth. So rather than resting on his triumph with relativity, he turned toward the harder task. Build a framework where gravity and electromagnetism, the two long-range forces known at the time, arise from the same foundation. That became his guiding mission. But despite decades of effort, he failed to close the gap. The equations of electromagnetism refused to blend with the curvature equations of general relativity. Gravity bent space. Electromagnetism relied on vectors and oscillations within that space. They shared no common mathematics that Einstein could extract. He tried rewriting field equations, stretching geometrical language to include electric and magnetic fields, but the pieces never interlocked. The frustration of seeing harmony in vision, yet contradiction in calculation, followed him for the rest of his career. Others were also struck by this puzzle. If the world must be unified, perhaps the road requires more than reshaping familiar variables. In the early 20th century, Theodore Kaluza proposed an idea that sounded closer to science fiction than accepted physics. What if space-time has more than 4 dimensions? Imagine adding a hidden axis beyond height, width, depth, and time. By doing so, the mathematics of general relativity could be extended. This 5th dimension, curled so small that no one could detect it, produced extra terms in the equations. Astonishingly, those extra terms matched the known equations of electromagnetism. It suggested that electricity and magnetism could simply be gravity playing out in unseen directions. This Kaluza-Klein model was shocking. It implied reality might be larger than our senses allow. The known 3 dimensions are only part of a deeper structure, with additional dimensions so compressed they hide from direct observation. Yet, if they exist, they could glue the puzzle of forces together. It was an audacious step. Few physicists at the time were ready to accept invisible dimensions of space. Still, the mathematics held a strange beauty, and it fired imaginations with the possibility that unification might come not by changing forces, but by enlarging the stage itself. To picture the challenge, think of puzzles you try to assemble on a table. You try forcing 2 pieces together. They almost fit, but the cuts refuse to line up. Push harder, and the cardboard bends. Then you realize the pieces are not defective. You simply lack the ones that fill the gap. The early attempts at unification were like that. Attempts to force gravity and electromagnetism together exposed missing parts in the set. Additional dimensions became those extra missing pieces. With them, the puzzle might lock in place. Still, the idea carried problems. The 5th dimension could be postulated, but there was no experimental way to prove it. No particle accelerator existed that could peer that small. No telescope could sense its influence. The theory was bold, but detached from evidence. For physicists who valued measurement as the ultimate judge, this status was troubling. Unification was a worthy dream, but without a test, it was no more than speculation. The model explained nothing new, predicted nothing measurable, and its assumptions rested outside what could be confirmed with instruments. Yet such failures often kindle progress. Even without data, the Kaluza-Klein concept pioneered an idea that would resurface decades later in string theory: the need for extra dimensions beyond the ordinary. The fact that later work adopted and expanded this feature shows the lasting power of speculative tools. Even when disproven, they can set the stage for future success. By daring to enlarge the scope of space, Kaluza-Klein introduced a theme that remains central to theoretical physics. It is worth stressing how radical this was. At that time, space was assumed to be limited to what we could see and measure. Suggesting the existence of hidden dimensions was like telling an audience that the stage they thought ended at the curtain, in fact extended far into darkness. And within that unseen space, new roles were playing out, shaping what appeared on the visible portion. Radical ideas like these do not succeed instantly. They clash with expectations, challenge comfort, and end up waiting for a generation that can reinterpret them. Yet, without them, science risks becoming trapped by its own caution. Einstein himself never fully adopted the Kaluza-Klein proposal, but it spoke to the spirit of his quest. He was driven not by convenience, but by ambition, the same drive that had led him to rewrite gravity's story. Even when his own calculations failed to blend the forces, the attempt showed that unity was not a luxury, but a guiding principle. The lessons of these unfulfilled attempts still matter. They remind us that progress does not only come from confirmed predictions, but from planting seeds of possible futures. As decades passed, these seeds bore fruit in unexpected ways. Later generations of physicists rediscovered extra dimensions, this time not just as a single hidden axis, but as many, folded and compacted in complex shapes. Those additions allowed vibrations of tiny strings to behave like the known particles of physics. The echoes of Kaluza-Klein's vision became part of a wider framework. What began as an isolated speculation became a foundation for more intricate theories. What matters most is the persistence of the dream. Even without proof, the notion of unity called out to physicists and drove them to extend the boundaries of imagination. Failure did not end the search, it sharpened it. History shows that daring to chase elegant patterns, even without immediate evidence, can shift the landscape. It stops science from resting too soon. It keeps the questions alive until tools evolve to test them. So the early struggle, with Einstein chasing a single equation and others proposing dimensions we cannot see, was not wasted. It gave modern physics its sense of direction. Today, when we hear of string theory and its hidden dimensions, we are hearing an echo of those first speculative steps. In that way, the dream of unity continues. The ambition of building a single coherent map of nature has not faded. If anything, the resistance of gravity has only hardened the resolve, and standing at this point, we see the natural step forward. From those early hints of unseen dimensions comes the first modern contender for unification. It no longer speaks in terms of point particles alone, but of something else entirely. Strings vibrating in patterns on the hidden fabric of space. Strings over points. What if the smallest ingredients of the universe are not dots at all? String theory asks us to consider that at the deepest scale, the building blocks of matter are tiny vibrating loops. They are not zero-sized points, as the standard model assumes, but extended objects, unimaginably small, stretched into filaments that can quiver like the string of a violin. Instead of treating an electron or a quark as a fundamental particle with no size, this theory claims it is one possible vibration of one type of string. In this view, the entire zoo of particles around us, electrons, neutrinos, photons, gluons, are the many musical tones of the same instrument. Each arises not from separate rules, but from different modes of vibration. Pause to imagine that. You draw a bow across a violin string and it produces a warm note. Tighten the string, change its length, or alter its tension, and the pitch shifts. The structure is the same, only the vibration differs. String theory proposes that matter operates on a similar principle. The frequency of a string's oscillation determines which particle appears in our world. A photon is one tone, a quark is another, and at least one special frequency gives rise to the graviton, the particle of gravity itself. The elegance is that gravity is not forced into the framework. It simply emerges as a natural vibration mode, something other unification attempts failed to capture. But this suggestion comes with requirements. A string has to vibrate in room to move around. In ordinary space of 3 dimensions, the mathematics fails. For the vibrations to produce all known particles and forces, extra spatial dimensions are required. These dimensions are not spread across the sky. Instead, they are compactified, curled so tightly that each point of 3-dimensional space we see contains loops of space folded inside it. We never notice them because they are packed to subatomic scales. Yet, according to the theory, they are everywhere, shaping the way strings resonate. Changing their geometry alters the menu of particles available. Those curled spaces are complex. They can twist into many possible shapes, each with its own physical consequences. In one configuration, we might see one collection of particle masses and forces. In another, the values shift. That variety leaves the theory with many versions, not one. It is a strength in imagination, but a weakness when predicting our universe. For critics, this flexibility makes the theory too open because almost any physical situation can be matched to one folded structure or another. The framework goes further by introducing new entities called branes. These are extended objects of different dimensions. A one-dimensional brane is a string, but 2-dimensional sheets, 3-dimensional volumes, and higher exist in the mathematics. Strings can end on branes or stretch between them. You can think of branes as higher dimensional stages where strings perform their vibrations. If strings are the notes, branes are the canvases on which sound reverberates. Their presence adds both richness and complexity. They expand the possible configurations of the theory, though they also make it harder to tie predictions to experiments. Another idea woven into string theory is supersymmetry. This symmetry links matter particles called fermions with force carriers called bosons. For every known particle, it suggests a hidden partner with a different spin. These partners help stabilize the framework, preventing collapse of its equations and smoothing out inconsistencies. Supersymmetry also appeals because it offers an answer to certain puzzles in conventional physics, such as why weak interactions are far less powerful than they might otherwise be. As elegant as the mathematics is, direct evidence for superpartners has not appeared. Colliders built to great size have searched for signatures, but none revealed themselves. This silence leaves supersymmetry as a plausible but unconfirmed piece of the puzzle. The challenge, as you might have noticed, is not conceptual beauty, but evidence. The strings hypothesized are far smaller than anything we can observe. To probe them with direct detection would require smashing particles at energy scales vastly beyond reach. One estimate puts the necessary accelerator at the size of a galaxy. Our most powerful machines today, vast rings beneath the Earth, are barely large enough to push into the deeper layers of the Standard Model. They cannot test whether fundamental strings vibrate at tinier scales. That limitation is sobering. It makes string theory, for now, a theory more of mathematics and thought than of direct measurement. Still, string theory provides something rare. It shows that unification of forces and matter might be possible if we begin from a new picture. It shifts our basic unit from a point with no size to a loop with extended shape. That change in perspective allows gravity to appear without forcing it, bringing together relativity and quantum mechanics under one roof. It is a conceptual victory, even if an experimental one remains out of reach. In that sense, string theory is like a blueprint for a bridge across a canyon we cannot yet build. We know the materials would work in concept, but our tools cannot raise the span. Skepticism has grown around this state of affairs, with so many possible versions of extra-dimension geometry with hidden branes and unconfirmed symmetries. Critics argue the theory risks becoming untestable. If almost any observation can be accounted for after the fact, then predictive strength has weakened. The challenge is to find a way of narrowing the possibilities to those that speak directly to the universe we occupy. Only then could string theory step from elegant mathematics into physical science. For now it occupies a liminal zone. Consider again how far this is from the standard model. In that older picture, each particle, a proton, an electron, a gluon, is fundamental. It is a distinct building block, unrelated to the others except by interactions. In string theory, they are not distinct at all. They are harmonics of the same vibrating entity. It is not a collection of fragments, but a single structure playing different notes. This is what makes the theory so captivating. It changes our view of reality into something unified at its foundation. The very diversity of matter could be one phenomenon expressed many ways. And yet it is distant. No laboratory can tune a string at this scale. No instrument can watch it vibrate. We can only explore its mathematics, test its logic, and hope that indirect traces might one day appear in cosmology, in subtle shifts of particle behavior, in gravitational signatures. Until then, string theory remains a beautiful candidate standing on the horizon, offering an elegant map we cannot yet step onto. The promise is unification. The cost is reach beyond experiment. That duality has defined string theory for decades, powerful in vision, elusive in practice. But despite this, the idea has transformed physics. It forced us to accept extra dimensions, branes, and supersymmetry as possible elements of reality. Even skeptics must confront the innovation it provides. It may or may not survive history's test, but its influence cannot be ignored. And this leads us naturally to ask, if strings are not the answer, what else could spacetime itself be made from? There is a rival approach that refuses extra dimensions and works instead with space itself chopped into discrete pieces, a framework called loop quantum gravity, where string theory stretches loops that vibrate. This other theory proposes loops that build the weave of spacetime itself. Spacetime in loops. What if the space you move through isn't smooth at all? Imagine shrinking smaller and smaller, past the scale of atoms, past subatomic particles, down to where distances lose their ordinary meaning. At that level, loop quantum gravity suggests space and time come in discrete packets. They are not endlessly divisible. Instead, space-time itself is built from indivisible units, like grains of sand composing a surface or pixels forming an image. To our eyes, the world looks continuous. But under the microscope of mathematics, reality may reveal a pixel structure, tiny, finite pieces of area and volume. This is the radical vision behind loop quantum gravity, often shortened to LQG. Unlike string theory, which replaces particles with vibrating loops, LQG keeps our familiar four dimensions of space and time and reshapes the background itself. Relativity treats spacetime as a continuous field, curving smoothly around planets and stars. LQG proposes that this picture breaks down at the smallest scales. The deep structure is a quantum web. The geometry of the universe is not a backdrop, but a product of fundamental quanta. The key tools here are called spin networks. Picture a graph of nodes connected by links, not random, but arranged by quantum rules. Each node represents a discrete unit of volume. Each link carries information about the way those units are connected. This web of relationships is not floating in pre-existing space. It is space. The links and nodes do not sit in space-time. They generate space-time by their structure. Just as atoms make up matter, units of volume linked by these spin networks make up the fabric we move through. Now let that network evolve. Over time, the nodes and links change and recombine. The result is called a spin foam, a dynamic version of the web, where space-time itself is in flux. A foam of possibilities defines how regions of space extend and interact. Instead of passive geometry, the universe becomes a quantum system of discrete building blocks. The smooth surface of relativity is recovered only in the limit when countless nodes and links blur into a fabric indistinguishable from continuity. To get a sense of this, think of a digital screen. When you look at a high-resolution display from a normal distance, images appear continuous. Zoom in far enough, and single pixels emerge. Each pixel carries one unit of information. Together they create the illusion of a smooth picture. Loop quantum gravity advances the claim that physical space works the same way. We see continuity only because our instruments are too coarse to notice the granularity. What looks like a curve in relativity could in fact be compiled from countless small quanta of area. The consequences of this proposal are far-reaching. If space and time come in discrete units, there is a smallest area and a smallest unit of volume that can exist. No measurement can divide them further. This introduces natural limits to what can be defined. Infinite density or singularities, the troublesome predictions of relativity, find resolution. A collapsing star under this scheme cannot shrink into a point of infinite curvature. Instead, the granularity of space halts the collapse. A black hole's center may not be an abyss, but a region where space-time units resist being compressed further. This expectation distinguishes LQG sharply from string theory. String theory requires additional spatial dimensions wrapped tightly at every point. Loop quantum gravity avoids this step. It stays within the four dimensions we observe, 3 of space, 1 of time, and quantizes them. That difference appeals to many researchers. The fewer assumptions you impose, the cleaner the theory appears. For critics of extra dimensions, LQG offers an elegant alternative, quantum spacetime, without new hidden realms. Another insight is how radically it changes our picture of time. If time itself is quantized, the flow we experience may be emergent. We are used to thinking of time as a continuous line on which moments slide past one by one. LQG replaces that line with discrete ticks. Between ticks, nothing stands. At the foundation, time is not flowing at all but emerging from the progression of spin networks transforming into spin foams. In effect, time may be as granular as space. This framework also changes how we ask scientific questions. In relativity, space and time form the stage upon which particles play. In quantum field theory, fields live in that background. But if the background itself is quantum, then the stage and the players belong to the same system. Physics no longer divides between the container and its contents. Instead, the geometry of reality and the motion of matter arise from one shared quantum structure. That is a profound shift in perspective. And like any shift, it comes with challenges. Calculating predictions in LQG requires handling complex networks of interacting quantum states. Unlike string theory's mathematics, with its continuous surfaces, this framework relies on combinatorial objects, networks that rearrange according to quantum rules. This difference makes it difficult to apply to familiar problems, yet the promise is strong. By quantizing geometry directly, LQG circumvents the infinities that plagued quantum attempts at relativity. It sets hard limits where the older theory breaks down. Consider again the analogy of a screen. Without pixels, an image could shrink to arbitrary resolution without limit. With pixels, resolution has an end. In relativity without quantization, curvature can steepen indefinitely until singularities appear. In LQG, granularity acts like pixels, halting the process at a minimum scale. That shift may resolve problems at the heart of cosmology, like the structure of the early universe or the interior of black holes. One question arises: if space is discrete, why can't we observe the granularity directly? The answer lies in the tiny size of the units, far beyond current instruments. The quantum of area or volume is unimaginably smaller than an atom's nucleus. To probe it would require energies well outside experimental reach. This leaves LQG in a similar position to string theory, rich in concept but short on direct evidence. The difference is that LQG does not require unknown dimensions or a zoo of possible models. Its assumptions remain closer to the familiar four-dimensional universe we occupy. For now, the testable predictions may come indirectly. The way the early universe expanded, the patterns hidden in cosmic background radiation, or the details of gravitational waves, these might carry marks of discretized spacetime. If a signal reveals a cutoff scale, or irregularities consistent with granularity, loop quantum gravity could win support. Until then, it remains a compelling model on paper. What stands out is how it reframes the puzzle of unification itself. String theory says matter, forces, and gravity unite as vibrations of extended objects. Loop quantum gravity says space-time itself is quantized, a lattice of relations, not a continuous sheet. Both break with classical intuition. Both shed the picture of point particles moving on a smooth backdrop. But the stories they tell diverge profoundly. So we have two contrasting visions. One describes threads vibrating in hidden dimensions. The other describes a network of quantum units making up the very coordinates we live in. Each offers answers to the collision between relativity and quantum mechanics. Neither yet has experimental confirmation. Yet both remind us the world at its root may be stranger than we imagine. In this way, strings and loops join in reshaping our ideas. They insist that the geometry of the universe cannot be taken for granted. Space and time, smooth and passive in earlier theories, now appear as structures subject to the same quantum laws as matter itself. Whether built from vibrations or from spin networks, the message is the same. Reality's foundation demands a new picture, and there is one place in particular where these radical visions must confront reality. A place where space-time and quantum scales clash head-on, pushing both theories to their limit. That place is inside black holes, the black hole laboratory. What if the darkest objects in the cosmos are also the brightest clues to nature's secrets. Across the universe, black holes mark places where gravity crushes matter into extremes. Light disappears, time stretches near the edge. To an outside observer, nothing can escape once it crosses the event horizon. These objects are visually silent, yet their silence tells us more about physics than almost anything else. For scientists searching for quantum gravity, black holes are not just strange remnants of stars, they are natural laboratories built by the universe itself. A black hole pushes the two pillars of physics into direct collision. General relativity explains how spacetime bends under mass, and its mathematics predicts that a black hole contains a singularity, a point of infinite density. Quantum mechanics insists that infinities cannot exist in physical reality. Instead, uncertainty and probability rule the smallest scales, preventing matter from being confined to a true point. Both theories work beautifully on their own, but in this environment they contradict each other outright. This clash is more than a philosophical puzzle. A singularity is not just an object we fail to see. It is a place where the equations stop making sense. If you tried to compute density or curvature at a singularity, you would not get high numbers. You would get error messages. The mathematics collapses into infinities that match nothing in the physical world. It is like entering calculations into a computer and watching it freeze when you divide by zero. Black holes are nature's way of forcing us to face that fatal error. At the surface of a black hole, the event horizon, strange things unfold. To relativity, the horizon is smooth, just another region of curved space-time. Nothing unusual happens locally as you fall through, except that escape becomes impossible. Yet, if you bring quantum mechanics into the picture, the story grows unstable. Near the horizon, virtual particles constantly emerge in pairs. One partner may fall in, the other may escape. Already we see a first hint of the huge tension between the theories. Relativity regards the horizon as empty structure. Quantum mechanics turns it into a restless region where fleeting particles test the rules of energy and time. The singularity at the center is still more severe. Here, relativity predicts collapse beyond measure. All matter compresses without bound into zero volume but infinite density. Quantum mechanics rejects such concentration. The uncertainty principle spreads particles into waves that cannot be pushed into one precise point. Which picture wins? Neither. At that depth, our current science reaches its limit. Nothing we have, not relativity or quantum theory alone, gives a complete story. For researchers, this makes black holes more than cosmic oddities. They are stress tests that break both maps of physics. You could ignore them only if they were rare or hypothetical. Yet observations have shown otherwise. Black holes appear after stars collapse. They populate the centers of galaxies. They merge and release bursts of gravitational waves across the cosmos. Their abundance means the puzzle cannot be avoided. Black holes confront us again and again, saying, "Your theories that work elsewhere will not do here." What makes them ideal laboratories is precisely this dual demand. They force relativity and quantum mechanics to act together, and in doing so, they highlight every flaw in treating them separately. No particle collider we build can reach such extremes. No lab on Earth can bend space-time in this way. Yet black holes perform the experiment by their nature. All we need to do is understand what they imply. Think again of the analogy of a calculator. Relativity is a calculator that handles planetary orbits and galactic dynamics without issue. Quantum mechanics is a calculator tuned perfectly to atoms and electrons. If you try them on black holes, both display the same result, undefined. You have reached the limits of their program. The crash is not optional. It signals the need for a new device, one that merges their strengths without failing at the border. Black holes highlight this as no other phenomenon does. This is why physicists turn to them for guidance. Their horizons, their intense centers, their predictions of infinities, all of these act like road signs pointing toward quantum gravity. If space is discrete, as loop quantum gravity suggests, the singularity may be avoided. If strings shape matter in hidden dimensions, then perhaps black holes reveal traces of those extra structures. Competing visions of quantum gravity make different claims about what happens inside or near the horizon. Testing those claims is not easy, but the environment of black holes provides the only natural setting where these questions cannot be ducked. And unlike distant theories of extra dimensions or hidden symmetries, black holes do not ask us to imagine in pure speculation. We observe them through gravitational wave events, by the motion of nearby stars, and now even with telescopes that capture the faint silhouette of their shadows. They are real features of the universe. This turns them into some of the only places where the dream of quantum gravity might leave detectable fingerprints. That reality makes them central to the search, not just interesting sidelines. But the greatest shock arrived when physicists discovered that black holes may not be entirely black. The event horizon, once thought a perfect prison for matter and light, could leak energy. This outcome arose not from relativity alone, but from recognizing that quantum fields surround the horizon. There, pairs of particles flicker into existence. One falls in, one escapes. The escaping partner robs the black hole of a tiny amount of energy. Over immense time, this drain adds up. The black hole, once thought eternal, evaporates. This insight is crucial because it marks the first clear sign that combining quantum mechanics with black hole physics changes the story completely. Relativity's infinite silence gives way to a slow glow, radiation born from quantum effects. Suddenly, black holes are not the end of the tale, but active engines of transformation. Their evaporation pushes us further into the territory of quantum gravity and forces us to rethink basic assumptions. So the lesson is that these dark objects do more than swallow light. They shine a spotlight on the fracture lines of modern physics. At their core, infinities collide with uncertainty. At their edge, particle pairs rewrite the law of what escapes and what stays. They are mistakes made real, contradictions embodied in astrophysical form, and because they exist in abundance across the universe, we must confront them again and again. By treating black holes as laboratories, we see that the search for quantum gravity is not locked in chalkboards alone. It is playing out in the cosmos, where extreme gravity and quantum fluctuation fuse into puzzles. To follow those puzzles is to step closer to the rulebook beneath both theories. And it is here, with black holes forcing new physics upon us, that the stage is set for one of the most startling breakthroughs of the last century. The discovery that something thought inescapable could in fact emit radiation. From here, we move to that paradoxical glow that reshaped how we understand the darkest object in the universe. When black holes glow, how can something that swallows light shine? A black hole is meant to be the final stop, the end of every possible path. According to relativity, once light or matter pass the horizon, escape is impossible. Nothing comes back. Yet quantum mechanics, with its constant jitter of particles in empty space, suggests a less perfect seal. When you mix these two views, you find that black holes might do the unthinkable. They can glow. The glow is not visible in ordinary light or radio waves. It takes shape instead as a faint trickle of radiation. At first glance, this seems absurd. A black hole is defined by its ability to trap anything. Its gravity bends paths of light itself. That is why it appears shadowed, even against the radiant gas around it. To claim that such an object could emit particles sounds like suggesting a perfect dam could leak. Yet quantum effects at the horizon turn that absolute barrier into something porous. The mechanism begins with virtual particle pairs. Quantum theory says even empty space is never empty. For split seconds, pairs of particles spring into existence, one particle and its antiparticle, and then annihilate, restoring balance. Normally, this activity leaves no trace. It is built into the fabric of quantum fields, but near an event horizon, the story is different. Here, the strong gravitational field can separate partners before they cancel. One falls inward past the horizon. Its twin slips outward. To an observer at a distance, the outward partner looks like genuine radiation escaping the black hole. This process drains the black hole's energy. Conservation of energy demands that the escaping particle's positive energy comes at the expense of the black hole's mass. It shrinks ever so slightly. Over immense spans of time, the loss adds up. A large black hole emits radiation so faint it would take longer than the age of the universe to evaporate noticeably, but smaller black holes bleed mass at faster rates. The smaller they get, the brighter they glow, until at last they vanish. Think back to the dam analogy. You believe a wall is perfect. It locks the reservoir without fault, but then you discover hairline leaks. Drops fall through, steady and persistent. The dam will not burst now, but given enough time, water levels will fall. The black hole, once thought permanent, works the same way. Its event horizon leaks through quantum effects. What looked eternal is in fact temporary. This discovery did more than reveal a new feature of black holes. It directly contradicted the classical picture offered by relativity. In relativity, black holes are stable graves for everything they consume. In quantum theory, no system can erase information outright, and energy fluctuations allow particles to arise and vanish. Combine the two, and black holes no longer stay silent. They evaporate. The two frameworks, instead of clashing into endless contradictions, here produce a startling outcome: radiation that bridges their domains. The rate of this process scales inversely with mass. A supermassive black hole at the center of a galaxy radiates almost nothing, effectively undetectable by our best instruments. But a black hole, the mass of a mountain, would release radiation far more intensely. A black hole smaller still, created in the early universe, could evaporate within our present age, bursting in a final flash of energy. Physicists have considered searches for such primordial remnants. If detected, they could provide one of the only practical proofs of this theory. You might ask, why haven't we seen Hawking radiation already? The obstacle is scale. The faintness of the emission from astrophysical black holes makes it vanishingly small compared to background radiation in the cosmos. Even if a telescope collects billions of photons, only a few might carry the unique signature we seek. Distinguishing them is like listening for the drip of one leaky faucet while standing next to roaring waterfalls. Yet the significance does not depend solely on observation. The concept itself changes how we think. It means black holes are not eternal prisons cut off from the rest of the universe. They are instead temporary structures, slowly giving back their mass and energy. Given enough time, every black hole evaporates. The universe's darkest objects are not final, but transitional. They participate in cosmic evolution. This evaporation also links black holes with the ultimate fate of the cosmos. If every black hole eventually radiates away, then nothing remains eternal. Even the largest galactic cores, which seem today like permanent anchors of structure, must one day vanish. Their energy will spread outward in faint radiation, mixed into the expanding fabric of space. The universe heads slowly toward heat death, an even distribution of low-level energy with no gradients left to drive change. Hawking radiation contributes to this endpoint. But the real power of this glow is not only its role in cosmic future, it is what it shows about the intersection of theories. To predict Hawking radiation requires quantum mechanics to describe fluctuations, general relativity to describe the horizon, and thermodynamics to connect the transfer of energy. For the first time, all three great frameworks of physics join in one prediction. Black holes radiate because reality cannot be split cleanly into separate laws. That makes them crucial laboratories for quantum gravity. Without needing a collider the size of a star system, the universe has given us objects that test quantum fields under the heaviest gravitational pull. Their horizons are fault lines where chance and curvature meet directly. The faint glow escaping their edges is more than radiation. It is a clue that our current theories need unification. And yet this gift also raises a deep problem. If black holes evaporate, what happens to the information inside them? Quantum mechanics insists information cannot be destroyed, though it may be scrambled. But relativity suggests the horizon hides everything permanently. If the black hole vanishes, does its information vanish too? Or does it hide encoded within the radiation somehow? This conflict is the next great paradox, born from the glow of evaporation. For now, what matters most is the shift in perspective. Black holes are not eternal one-way doors. They leak slowly, radiating energy into the cosmos. Their existence forces us to step beyond the neat boundaries of earlier theories. They prove that our current understanding is incomplete, but they also guide us toward the missing pieces. So, the riddle continues. A black hole's darkness is not complete after all. It shines with a faint but unstoppable glow, hinting at the laws beneath relativity and quantum mechanics. And as we follow that glow, we arrive at a deeper puzzle still, the fate of information swallowed by a black hole, and whether any detail of the past is ever truly lost. The puzzle of lost information. Where does information go when a black hole evaporates? The question cuts to the core of physics. Quantum mechanics lays down a strict rule. Information about the past cannot be destroyed. However scrambled, however dispersed, traces of it must remain. General relativity, combined with Hawking's discovery of radiation, seems to disagree. If a black hole takes in matter, then releases only random-looking radiation before vanishing, every trace of what entered appears erased. That conflict has come to be known as the black hole information paradox. To understand why this is so severe, recall how black holes radiate. Quantum fluctuations near the horizon produce particle pairs. One falls in, one escapes. The escaping particle carries energy away. Over vast timescales, the black hole evaporates and eventually disappears. But Hawking's calculation shows the radiation carries no detail about what formed the black hole or what it swallowed later. It is featureless, like heat radiation from a hot surface. That leaves us with a contradiction. Quantum mechanics demands conservation of information. The radiation as originally described shows none. Something does not add up. A simple analogy helps. Imagine burning a book. The paper is destroyed, the words are gone to the eye. But in principle, the smoke and ash still encode all the information. If you measured every particle of soot, every puff of gas, and how they scatter, you could in theory reconstruct the words. It is impractical, but not impossible. In physics, that retention of information is crucial. Nothing is lost, only rearranged. But if a black hole destroys information outright, it breaks this rule. Unlike the burned book, where faint traces exist, the evaporated whole would expunge details completely. That breach would mean the laws of quantum mechanics are wrong or incomplete. For many physicists, that possibility is unacceptable. Quantum mechanics is one of the most successful frameworks in science. Its predictions match experiment to astonishing accuracy. To discard its central principle, information conservation, would dismantle countless results. But relativity, too, has proven nearly flawless at scales where gravity dominates. Neither side can be abandoned lightly. The information paradox, therefore, exposes an open wound between the two pillars. Mathematically, the puzzle takes a stark form. A pure quantum state describes what falls into a black hole. Over time, Hawking radiation leaks out. The calculations show that radiation represents a so-called mixed state, random, thermal, stripped of the fine details of the original input. If pure states evolve into mixed states, then quantum unitary evolution, one of the most fundamental properties of the theory, is violated. Such a break would rewrite the core of quantum mechanics itself. Scientists have tried to find escape routes. Maybe the information is not destroyed, but hidden. Perhaps subtle correlations exist in the radiation, faint patterns buried under apparent randomness, encoding details of the swallowed matter. If so, the paradox is resolved. But proving the presence of such correlations has proven difficult. Hawking's equations define the radiation as thermal, with no imprint of detail. Amending that without breaking consistency elsewhere is challenging. Other proposals take a more radical path. One is the firewall paradox. It suggests that perhaps the horizon of a black hole is not benign and smooth, as relativity indicates, but in fact a wall of violent energy. Any particle crossing would be obliterated instantly, breaking the gentle picture of spacetime. In this vision, information is incinerated at the boundary, not at the singularity deep within. That could explain why nothing emerges later, but the price is steep. It breaks the long-trusted principle that a falling observer experiences nothing special at the crossing. Firewalls clash directly with relativity's insistence that local physics near the horizon is normal. So we face competing impossibilities. If infalling matter leaves no trace, quantum mechanics is overturned. If a firewall exists, relativity is overturned. Each proposition saves one theory only by damaging the other. The paradox does not permit quiet compromise. It demands a deeper change. You can feel the tension as you imagine the scenario. Picture someone tossing matter into a black hole, say, a computer filled with information. Later, the black hole evaporates. If you collected the radiation particles, they look like random heat. Where is the code that once filled the computer? Did it leave in disguised form spread across the radiation's fine structure? Or is it gone, stripped from the universe? For conventional quantum theory, the second option is forbidden. Yet relativity suggests exactly that. Some approaches, like string theory, try to bypass the paradox by proposing that the black hole is a state of strings which can encode information in their extended structure. Loop quantum gravity suggests that spacetime's granular units prevent true singularities, allowing information to be released in some altered way. Other researchers imagine that space and time themselves are emergent. In that case, information might not sit in spacetime at all, but in some deeper level of physical law. The debates leave one conclusion: solving the paradox may require reinventing the fabric of spacetime. Trying to patch each theory in isolation has produced contradictions like firewalls or non-unitary evolution. But a united framework, one that contains both gravity's geometry and quantum probability, might rebuild the rules so the paradox dissolves. The question is not only about black holes, it is about whether physical law preserves information in every process, everywhere, always. The severity of this problem cannot be overstated. It is not a minor technical glitch. It is the deepest conflict in modern physics. At night, the universe contains countless black holes, each holding secrets about what fell in. If evaporation ensures those secrets vanish from existence, then the world itself erases history. If that erasure never occurs, then our current mathematics is hiding the trick. No other puzzle cuts more directly to the foundations of science, and it affects how we think of the universe as a whole. If black holes radiate, then die, our cosmos is filled with remnants of lost events. If information survives, perhaps encoded in subtle data spread over a horizon or stored holographically, then the universe is faithful to its past. Either way, our picture of reality changes. We must accept either a break in relativity, a break in quantum mechanics, or a new principle uniting them both. So we are left with a paradox that forces progress. Black holes, instead of silent endpoints, drive us to reimagine law itself. They demand we ask whether space and time are the true foundation, or whether another layer of description holds the key. Resolving the information paradox is not a side project. It is the central challenge, one shaping the path to quantum gravity. And at this point, a daring proposal enters the conversation. What if all the information swallowed by a black hole is not lost at all, but stored in a different way, on a surface, not inside the volume? What if the universe itself works that way? A three-dimensional world projected from two-dimensional data, a hologram, the holographic universe. What if everything we see around us, the walls, the trees, the stars above, is not quite what it seems? The holographic principle asks us to consider that the three-dimensional world we move through could be a projection with all its information encoded on a surface of lower dimension. To imagine this, picture a sticker you have seen on a bank card or an ID. Flat to the touch, but when light hits it, you see a pattern that looks three-dimensional. Every detail of depth is contained on that thin sheet. The claim here is similar. A region of space, however vast, may be fully described by information inscribed on its boundary. This principle came not out of whim, but as a response to the black hole information paradox. When Hawking showed that black holes radiate, the implication was that information might evaporate with them, but the holographic principle suggests otherwise. Imagine the event horizon, the spherical surface that marks the point of no escape. The idea is that every bit of detail about the matter and energy inside is recorded on that two-dimensional surface. The horizon becomes a ledger. As radiation flows out, the lost information could be stored or encoded in correlations on that boundary, ensuring nothing is destroyed. The tension here is sharp. Relativity alone treats the interior of a black hole as smooth space-time ending in a singularity. Quantum mechanics insists that information never vanishes. The holographic view offers a path that keeps both intact. It says, yes, the interior looks three-dimensional, but in truth it is fully mirrored on the two-dimensional horizon. If so, then the paradox dissolves. Information is never lost because it was never inside alone. It has always been encoded at the edge. The more general claim extends beyond black holes. Any finite region of space, any volume you point to, could be described not by millions of tiny bits scattered through its bulk, but by data arranged on the outer surface of the region. It turns the usual perspective inside out. Instead of the surface being less detailed than the interior, the surface might hold the complete description. Depth might be an illusion born from two-dimensional patterns of quantum information. A specific version of this principle is called ADS/CFT correspondence. In this mathematical duality, a theory of gravity in a higher dimensional curved space, anti-de Sitter space, matches exactly to a conformal field theory without gravity living on the lower dimensional boundary of that space. What happens in the bulk has a counterpart on the edge. A calculation impossible in one picture can be translated and solved in the other. This correspondence shows that gravity and quantum theory may not be separate at all, but two languages describing the same physics. The striking point is that the duality is precise. Every state in the gravitational theory has a one-to-one partner in the boundary quantum theory. That means that to study black holes or curved spacetimes with gravity acting, we can switch to a framework without gravity, one that uses well-tested tools of quantum field theory along the boundary. It is as if a puzzle in 3 dimensions reduces to a solvable pattern on a flat sheet. The physics in depth is replicated by the physics at the edge. Think again of the sticker hologram. Tilt it, and a shifting 3-dimensional image appears from a perfectly flat sheet. In reality, every ridge of image, every shade of depth, is calculated from the arrangement on the surface. The holographic principle says the universe might be built with the same trick. What we experience as 3-dimensional space may be the collective result of information encoded on a lower dimensional boundary. This flips our usual sense of what is fundamental. We tend to treat distance, volume, and depth as basic features of the world. But here, space becomes emergent. It arises from the entanglement and structure of information itself. Space-time might not be the foundation, but the outcome. In that case, geometry, as Einstein described it, would be a large-scale reflection of quantum data patterns we do not see directly. What makes this powerful is its ability to resolve puzzles. The information paradox is no longer a contradiction. The holographic account says the data was never lost in the first place. As a black hole evaporates, the apparent randomness of its radiation might still carry subtle influences of the encoded information on the horizon. It looks thermal, it looks uniform, but hidden correlations could carry the bookkeeping of everything the whole swallowed. The holographic principle goes further. If space-time is emergent, then time itself may be an artifact of information flow. Quantum entanglement, the tying together of states across distance, may create the illusion of connected spaces. As entanglement patterns shift, the very contour of space could warp. This makes geometry not a fixed background, but a shadow of deeper processes at the information level. For us, the consequences are direct. Reality as we perceive it may not be built from things in space. Instead, what we call space might be built from relations among data. In one view, space is pixels, as loop quantum gravity suggested. In another, space is a projection from encoded quantum detail on a surface. Both reject the old idea that geometry is the silent stage. Both treat it as an emergent property. The holographic version emphasizes information, entanglement, and boundary bulk relationships as the true foundation. Testing such a wild proposal is difficult. You cannot walk to the boundary of the universe to search for inscriptions, nor can you probe event horizons directly. Scientists instead look for indirect traces. They model black holes using ADS/CFT and compare results to known properties of strongly interacting particle systems. They explore patterns in the cosmic microwave background for signatures of holographic encoding. They examine gravitational wave records for deviations consistent with information escaping. These are delicate, indirect moves. The evidence is not yet decisive, but the framework provides guidance for what anomalies to search for. The holographic principle remains a proposal, not confirmed law, but already it has reshaped theory. It allows researchers to handle problems of quantum gravity in controlled form by translating them into boundary theories where established techniques exist. It shows that contradictions about information might be solvable without discarding either relativity or quantum principles. And it suggests, as a side effect, that the universe is stranger than we assumed. Stand back and absorb what this implies. The solid three-dimensional world you walk through may not be the basic level of description. Instead, you may inhabit an emergent projection of deeper, lower-dimensional data. Every step, every object, every interval of time could be the outcome of quantum information coded across boundaries we cannot see. It is unsettling, but it fits the clues left by black holes, by radiation, and by paradox. That redefinition changes our view of what reality is. Space and time move from the category of fundamentals to the category of appearances. They may be no more fixed than a rainbow, real in experience, but arising from underlying structure. And if that holds, then to understand the universe we must study not geometry, but information. But even if the idea is elegant, the challenge remains. How could we ever test whether the universe itself is holographic? What instruments could measure such a claim? The search now turns back to the cosmos, to faint patterns in ancient light and ripples in space-time, in hopes of finding the subtle marks of projection. Clues written in the cosmos. In science, some frontiers are closed not by lack of ideas, but by limits of energy. Quantum gravity is one of them. To test it directly would require colliders powerful enough to reach the Planck scale, far beyond anything we can build. Our best particle machines fall short by an enormous margin. That barrier means the quantum structure of space-time cannot be probed head-on in laboratories, so we look outward instead. We search for natural arenas the universe itself has built, moments and places where the conditions were harsh enough to bring quantum gravity into play. The most obvious place to look is the early universe. In the first second after the Big Bang, densities and energies soared. Here quantum gravity was not a rare effect tacked onto classical physics. It must have been the rule. Yet we cannot see that era directly. What we can see is its fossil light, the cosmic microwave background. Frozen into that faint radiation are patterns seeded by the earliest moments. Small irregularities in temperature and polarization act as fingerprints. If quantum gravity left a mark, it will be hidden in those patterns. Think of the microwave background as a faded photograph. The image is grainy and blurred by time, but details remain. Each hotspot or cool patch is more than a visual blemish. It is a trace of physics carried forward across 13 billion years. Measuring those traces with precision instruments already tells us about cosmic expansion and matter content. The hope is that deeper, subtler marks are there as well, subtle striations pointing to quantum gravity. Another window comes from gravitational waves. These are ripples in space-time itself, produced when massive objects accelerate. The merging of black holes or neutron stars sends tremors across the cosmos. Instruments that measure tiny changes in distance, fractions of the width of a proton, have already captured these waves. What matters for quantum gravity is not just that the waves exist. It is how they behave as they travel. General relativity predicts precise patterns. Any deviation, however slight, could reveal new physics. In a sense, gravitational waves are messengers carrying records of their birth. They travel vast distances almost untouched, bringing a clean signal from wild events. If those signals show distortions, unexpected frequency shifts, altered damping, or extra resonances, they could hint at spacetime not being the smooth continuum predicted by relativity. Instead, they could indicate that granularity or information constraints, effects expected in quantum gravity, were at work. The same idea applies to black holes themselves. While we cannot approach their interiors, we can watch their behavior as they collide and ring out. The waveforms from these events act like voices. They contain tones of frequency and damping that reflect the structure of space around the holes. If those tones differ from what relativity predicts, slightly off-pitch or lasting longer than expected, the discrepancy could be evidence of quantum effects. Detecting this requires immense sensitivity, but even small anomalies matter. These clues are faint. They demand instruments of extraordinary power and subtlety. The cosmic microwave background requires telescopes capable of distinguishing millionths of a degree. Gravitational waves demand interferometers responding to displacements smaller than atomic nuclei. That is the scale of challenge. But it is also what thrusts quantum gravity into observational science, rather than leaving it in the realm of pure thought. We are building tools that test it indirectly. Particle colliders might still play a role. While they cannot reach Planck energies, they can search for hints. If extra dimensions exist as string theory proposes, their presence might alter particle interactions ever so slightly. If gravitons exist, faint traces might appear as missing energy signatures in collider data. To date, none has been found, but as technology pushes forward, the possibility remains. The strategy is clear. We cannot climb the mountain directly. We must look for its shadows. Patterns in cosmic background light, ripples in gravitational waves, unexpected anomalies in particle collisions, all serve as shadows of the deeper structure we cannot touch. By spotting where the patterns deviate, we infer what underlies them. There is also Hawking radiation. In principle, measuring the evaporation of a black hole would give direct information about the reconciliation of gravity and quantum fields. In practice, large black holes evaporate too slowly to notice. A cosmic black hole, the mass of the sun, radiates faintly, much fainter than the ambient microwave glow of the universe. Yet, if smaller primordial black holes exist, relics from the early cosmos, they might be evaporating now. Explosions of energy from such events could reveal themselves as bursts across the sky. Detecting one would be like discovering a natural particle collider. that reaches Planck conditions without our intervention. In each of these cases, the challenge is not lack of theory, but scale. The effects are buried under noise. Searching for them is like listening for one flute in a storm of drums. It requires precise filtering, patience, and instruments far beyond those of earlier generations. But already progress has been striking. Cosmic background surveys have mapped the sky with stunning precision. Gravitational wave detectors record collisions of distant black holes. Our sensitivity to faint signals has grown from fantasy to engineering. We should not pretend that answers will come quickly. The traces of quantum gravity are likely subtle, perhaps only apparent after years of data. Yet this does not nullify the search. Instead, it transforms it into a long project, gathering evidence piece by piece. Every anomaly, every unexplained deviation becomes a lead to follow. For us, the implication is profound. Quantum gravity is not forever confined to chalkboards or to unreachable scales. The cosmos itself offers records of its action: radiation from the first second, waves from violent mergers, signals hiding in the shine of black holes. Each opens a path for evidence in a field starved of it. Instruments may yet find the fingerprints, a twist in a wave, an irregularity in a cosmic map, a flash from a dying black hole. Each would signal the missing unification we seek. They would move quantum gravity from a theory of speculation into one of measurement. And so the paradox shifts. The universe denies us direct access to Planck scale, but it leaves stories written in its oldest light and strongest collisions. Our job is to learn how to read them. That pursuit is not guaranteed, but it pushes us closer to the boundary where forces, particles, and space-time converge. The starlight crossing the cosmos, the microwave glow left by the first second, the ripples rolling through space, all may already contain the clues we need. And if the writing is already on the sky, the question becomes not just how to detect it, but what it means for our place in a reality where space and time may not be fundamental at all. Black holes and the Big Bang once looked like failures of physics. Equations broke down, infinities appeared, and predictions lost meaning. But instead of contradictions, these extremes now act as signals, natural laboratories that show where the missing theory must lie. Quantum gravity forces us to consider that space and time are not foundations at all, but products of deeper processes. If so, geometry and flow are stories we use to describe patterns beneath. This search is not just physics. It is a quest for the blueprint of existence itself, an attempt to uncover what reality is truly built from.